So, great pleasure. DK Panda is going to give a session now that talks about more AI training. And then the next talk, I think it's tomorrow, right?
Tomorrow, yeah.
We'll be more focused on MPR and stuff. Please welcome DK Panda.
Okay. So good morning again. Thank you, Gilad and Hussein. Again, as I was telling, I came, the first talk I gave here in 2011. At least based on my counting, again, I might be wrong. This one is the 24th talk. So tomorrow it will be 25th. So we'll be covering in the 10 years, 25 talks. But today so it's always a pleasure to come and interact with all of you and try to bring the latest and greatest what we are doing in my group. So today's talk will be focused on, as you see the title, Scalable and Distributed Deep Neural Network Training on the modern HPC systems. So as many of you know, we are in the exciting field of the deep learning. As many of you know, the deep learning is a very smaller part of the bigger AI. So if this is the AI, then we have the machine learning as a smaller subset, then we have representation learning, and then the deep learning. A lot of times people mix and match these terminologies from a technical point of view. This is how things look like. And of course, this deep learning is a lot of interest. I also want to say that there is a lot of hypes also because the field is evolving. Just like any one of you, these days also when I write papers with my students or write proposals, I need to make sure that the deep learning word is there, okay? Otherwise the chance goes down significantly. So if you just put these two words, AI or deep learning or machine learning, you are in a good position. But the broad idea is that a lot of these concepts were there since 1980s. It is not just now people are discovering, but what is happening is the computability of the DNNs. That's what has changed over the years, so that we are newer technology, we are able to actually validate what people have been thinking for all these years. So this is just a little bit of market trends, saying how people are thinking, the world markets from 2016, how the things will be changing in the AI in terms of the revenue. But more importantly, are these areas. This is where a lot of explorations are happening, how the deep learning or AI can actually help all these fields, starting from contract analysis to object detection, navigation, to text query of images, content distribution, predictive maintenance, scalable processing of medical data, static image recognition, even the commercial trading kind of things. So all these fields, people are trying to explore how the machine learning can help. So in that context, so this is the nice synergy what is taking place between these three subfields, HPC, big data, and then the deep learning. And each subfield is actually trying to put more pressure on the other subfield. Okay, so for example, if we design some good HPC systems, of course people are trying to design the big data analytics stacks to run on the HPC systems. Then using that, both HPC and big data, people are trying to do deep learning. And once you are trying to solve some of these problems, then you are actually trying to go into the next stage. So in that context, we again need a next generation of the HPC machine. So I tell my students, doesn't matter in which of these areas you work on, next 10 to 15 years, as long as this positive cycle remains hold, you are in good position. You have jobs, okay? I hope in the next 10 to 15 years, I don't see it is going in the reverse direction yet, but you never know, it may happen. So these kind of things, so what is happening more on this convergence, like how do you do the convergence kind of things between these three subfields? I'll go more into that in tomorrow's talk, but today I'll be more focusing on just the deep learning aspect. And not only like these issues are there on dedicated systems, of course also people want to run these on the cloud also. Like the similar kind of the workflows we heard from Sadaf, new kind of workflows are coming and people are trying to propose different kinds of services there. So with these three subfields, earlier people were just thinking this separately, like you think separately HPC, big data and deep learning, but now some newer kinds of workflows are evolving. So you can think of changing the workflow from one domain to the other subdomain. So here it is like, let's say, data analytics pipeline from Flickr. So you can think that you are preparing some data sets at scale, then you are trying to do some deep learning at scale, then you might try to also do non-deep learning at scale, then apply machine learning. So you can mix and match your workflows based on your requirements. So you can be totally imaginative and see how you can actually take advantage of these three subfields or subdomains to the best of your advantage. And of course, in this context, we also want to exploit data locality, and also we want to design the systems which are more cost effective. So in this context, if we take a look at like the HPC systems, this is what we see. Most of the systems are trying to be designed like a multi-core processors, of course, high performance interconnects like InfiniBand, and then accelerators. And the next wave, whatever is coming, is these NVMe SSDs. So I think that's what you will see in the next 5 to 7 years. A lot of things will change, especially on the I/O file system side, to handle the big data, because these newer kinds of RDMA-enabled SSDs are coming. So in this context, like when you go into the deep learning, now of course there are two phases. I'm sure most of you are familiar with. One is the training, then is the inference. And most of the time is the training, which is the most compute and communication intensive process. It can take days to weeks. And this is where the field has been working very heavily for the last several years to make the training faster and faster. And whatever used to take some days or months, the question is like, can we do it in terms of like some hours, okay? And inferencing is gradually coming. So far it is not an HPC-centric problem, but there have been some applications or some people are exploring, even that inferencing also can be a high throughput kind of computing, not the pure HPC, but let's say you are doing inferencing of a lot of things at the given time. So that can be like a high throughput computing. Need not be like you are not trying to accelerate a single inferencing job, but over a lot of jobs, you are trying to handle it. So today's talk, I'll mostly focus on the training. Now, of course, the training, as many of you know, like every time you have a newer hardware, newer kind of a infrastructure, whether it's a CPU or a GPU or an FPGA, you can actually try to accelerate the things, but of course there is a limit, what you can do with a one unit. And this is where the question is like, can we use more GPUs or can we use more nodes? And this is where the need for the parallel and distributed training comes in. So how many of you are just involved in this kind of activities? I just want to see how many have done some DNN training. Okay, few of you, that's good. Okay. So then this is like a broad roadmap. You can say like the community has been thinking about both scale up and scale out. So that means within a node, as you might have seen, like sometimes you put like a 2 GPUs, 4 GPUs, even 16 GPUs together. So the question is, as I am putting more GPUs, am I able to get good performance? So that is like this y-axis, which is scale up. And then of course there is a limit what you can do with so many GPUs, and then the question is I need to go to more number of nodes and more number of GPUs, that is the scale out, okay? And obviously, as the year progresses, we want to go to this corner. That means we want to get the best scale up and then get the best scale out. And this is where different people have been working on different things, like for example, NVIDIA has been working on CUDNN, Intel has this MKLDNN, NVIDIA also has this Nickel 2 library. People are going through MPI solutions. People are also going through big data solutions. So always like things are converging, and then hopefully like in the next few years, you will see a lot of solutions will get matured so that we can get the best scale up and the best scale out. Okay? And this is exactly in my group also we are taking the approach on trying to enable this community in all these different directions so that they can get the best performance. But then what happens, like many times you would have seen, like the people trying to have this kind of a solutions, like, okay, I can do so many images per second, I can keep on increasing. But then if you take a look at all the stack, this is how the typical stacks look like, okay? At a bottommost, you have the hardware. I mean, this is the typical like a processors or many core GPUs, and this is where like the top applications are, the DL applications are lying, image recognition, speech processing, etc. And this is where the most of the frameworks lies. These are the deep learning frameworks like Caffe, TensorFlow, CNTK, etc. And to facilitate those frameworks, this is where a lot of actions takes place, like these are the kind of a convolution layers or optimized convolutions layer or CUDNN layers are there in these frameworks. And most of these are a lot of linear algebra operations, okay? So traditionally, if you remember, even in the HPC side, there have been a lot of these kind of BLAS libraries, and similar kind of things are also being used here, like Atlas, OpenBLAS, MKL 2017, or CUDNN. So the idea here is that many times when people put these numbers, they might not be doing a holistic evaluation, okay? So that's what I want to focus here. So purely from a technical side, if you want to show some numbers, you need to make sure that everything is captured there. So that means you are using the best hardware, best BLAS libraries, all the best convolution layer, then only you can say that, yeah, this is the latest results. If you just skip some of these layers and then just focus on only one layer or the one or two layers, then you may not be getting the complete answer, okay? So in fact, that's what we did. In fact, this was a paper we published at the ML-HPC workshop 2 years back, held in conjunction with Supercomputing 2017. So just to show how you can really present technical details about the DNN training. So if you are interested, you can take a look. But what I'll try to focus here, the main challenge is how these two fields can be combined. The high performance computing, I think HPC, which many of you are familiar with, and then the deep learning frameworks. So how we can bring these two things together. So in this context, at least from my group's perspective, we have identified 4 different directions. So that's what I'll try to highlight. So the first thing is that when you take all the deep learning, machine learning frameworks like CNTK, Caffe, Caffe2, TensorFlow, these can be actually considered just like traditional HPC applications. If you're an HPC system designer, these frameworks like your application, okay? But the actual applications may be sitting on top of these frameworks, okay? So inside these frameworks, of course, there are a lot of these kind of issues happen, just like any other HPC application, your memory requirement, compute requirement, the communication overhead. So the question is you need to ask, are these frameworks all optimized or not? That is the kind of the first challenge. And if not, you need to optimize those frameworks first. Then the second is, once these frameworks are optimized, then of course we want to run this distributed training, and then how do we design these communication runtimes? Okay, because now we are going to more number of nodes, and of course there are communication overhead, and how do we design these runtimes? And this is where like the different kinds of things come up, like the network and then the HPC cluster as well as the GPUs. Then the third challenge is like the new design challenges happen, like inside this again runtime. Of course, you have to accelerate like point-to-point operations, and I'll gradually introduce, there are a lot of collectives operations at here. Most important is the all reduce. I'll go into a little bit more details, and that's what you need to optimize. And also, there is some concepts of CUDA awareness. So if you can just use that, especially for the GPU cluster, you can also get good performance. So that is kind of the third challenge. And then the fourth challenge, just like HPC, can we do some co-designing across these layers? Because these are coming from different, the framework is, some people are doing the framework, some people are doing application, some people are doing runtime. So the question is, can we, instead of looking at a layered manner, can we consider also some co-designing approaches so that we have a very highly optimized and integrated stack, and then trying to get the best performance. So in this context, in my group, we have been working on multiple directions. That's what I'll try to share some of the results. So I'll first try the MPI-driven deep learning, and I'll try to focus on both CPU-based and also GPU-based. There are two communities here, both CPU and the GPU. Intel is pushing the CPU, and NVIDIA is pushing the GPU. So we are trying to help both these directions to proceed. And then I'll try to go into a little bit of co-designing these deep learning stacks with high-performance MPI. Also, I'll try to indicate like some out-of-core DNN training. So this is a newer problem which is coming, just like we had earlier in the HPC, out-of-core issues. That means you cannot fit everything in CPU memory. So now the problem is coming, everything you cannot fit in the GPU memory. So how do you handle this kind of solution? So I'll first try to focus on this, and then I'll go into a little bit more on the other directions, like accelerating TensorFlow, traditional TensorFlow, like people are using TensorFlow with gRPC. So how we can accelerate that, accelerating big data stacks, and then also accelerating deep learning over big data. So I'll gradually cover these things one after another. So now the question is like, when you go into the distributed training, so let's take an example. This is a very common framework kind of things. Let's say in the beginning, you have to push your data into the GPU. So this is like the data propagation. You have a GPU cluster, you have to push the data into the GPU before the operations can start. So here you can see there's a very common operation you have to focus on, which is the bcast or the broadcast. And MPI broadcast has been there in the HPC for many years. So now the question is, the broadcast, again, people have optimized for all different message sizes. And here you need to focus on optimizing it for very large data, because this is where the batch sizes and all the different things you try to push into the GPU memory. So then you try to do this forward and backward pass. These are the deep neural networks. But then after you try to do some iterations, this is the most important thing, you try to do reduce. Okay? And some of you might be knowing this is like the gradient aggregation kind of things you do. So that means the neural network is being trained, and then you need to take all the results, and then you're trying to see whether things are converging or what is the accuracy, and then you keep on iterating. Okay? So in this context, again, this becomes important operation, MPI reduce. And if you are an HPC person or if you're an MPI library designer, again, this is nothing new. It has been there for many years. MPI reduce, MPI all reduce, all these collective operations has been there for many years, and people have been optimizing this. But now, depending on your framework, you might be seeing that now you need to optimize these operations for very large messages. That was not there earlier. In the HPC, traditional HPC PUC, you do an MPI all reduce. In the end, you may need to optimize for 8 bytes, 16 bytes, 32 bytes. But now it might be happening like 8 gigabytes or 8 megabytes kind of thing. So you need to rethink your algorithms to do these kind of operations in the best possible manner. That is one way. But again, since the field is evolving, the current frameworks are trying to use a lot of large messages, but there is already work taking place saying you need not always use the large messages. You can also use some medium messages, small messages. Those are also important in this domain. So the question is, we need to optimize for all these message sizes. So that is the kind of like the link between HPC and then the deep learning. So it is not like the deep learning is trying to bring some new things. HPC people have been working on all these things. Now you just need to rethink and see how to fit it with the deep learning. So in this context, let me introduce our MPI project. Many of you might be familiar. This is like the MHAPPIS project. I'll go into more details tomorrow. So this is the project we started almost day one of InfiniBand. When the InfiniBand was introduced in year 2000, prior to that, we were working on MirrorNet, Quadrix, those kind of technologies. So we're the very first ones. In fact, in the supercomputing 2002, we were the first MPI, which was trying to run on InfiniBand. That time, it was only 8 nodes, and we are struggling to run an MPI on 8-node InfiniBand, 2002. Okay? If some of you attended the SCO2, that was the kind of the challenge. And of course, we have come quite a lot in the 18 years. So I'm very proud of my team. So this is an 18-year-old project continuously going on. And of course, we have different versions. I'll talk a little bit about that in the next few slides and tomorrow. So currently, these libraries are being used by more than 3,000 organizations in 88 countries. These are, again, based on voluntary registrations. A lot of people download without identifying. That is perfectly fine with us. We crossed, last supercomputing, we crossed more than 500,000 downloads just from our website. Of course, our libraries are integrated with a lot of other stacks like Red Hat, SUSE, OpenHPC, vendor-supplied stacks, so we don't keep tracks. These are the number of downloads just from our site. But more importantly, these are being used in all these large top 500 systems. And we have been in this community almost over a decade, really trying to help all these systems. And this is the next system which is coming up in the US academia, Frontera. How many of you have heard of this system? Okay, some of you. This is from the Texas Advanced Computing System. This will be the center. This will be the first large-scale open science research systems. Of course, we have Summit and Sierra, but those are the DOE kind of things, but this will be for academia. It will be around 35 to 40 petaflops. So I'm a co-PI there, and you will see this machine will be coming out online in the next few months in this summer. So this is the overall architecture of our MPI stack. Of course, we traditionally focus on MPI and PGAS, and we focus a lot of different networking technologies and multi-core, many-core architecture, and these are the runtime. But through this stack, not only we are trying to satisfy HPC, we're also trying to satisfy the deep learning. That's what I'll be talking about. So the same stack, not only you can use for HPC, you can also use it for the deep learning applications. So I'll try to first start with the CPU-based deep learning. So we have different versions of the MAPIS2. This is the base library, then there is an advanced library, then there is a GPU optimized, then we have things for cloud, energy aware. I'll not talk about all those things. But this is where we are trying to stress on the CPU-based learning. So many people again can ask saying, okay, why CPU-based learning? Of course, CPU-based learning is not very fast. But the thing is, many people have access to those. Okay, yeah, many times you have large cluster, the CPUs. So if you are trying out some deep learning application, you can always use. And of course, the GPU-based learning will give you very good performance, but they are expensive also. So many times, like might be in the universities, those kind of environments, you may not have full access. So once again, what we are trying to do here, as I told you earlier, like the collectives. So this is where we are trying to heavily optimize these collectives, like the reduce, all reduce, bcast, those kind of things. And especially here, we have introduced a scheme. There is a new scheme which is coming called XPMEM. How many of you heard of this terminology? Okay, some of you, that's good. So this is like the runtime. This is a mechanism. It's like a cross-partition memory. So you can actually specify the address of one process being accessible by the other one. Or you can register and then pass the pointers, so you can do very fast communication. So we have brought that into our library. This is the XPMEM-based support. So this is already available in our MAPIS2X release. So through this, you can see, like, since using this mechanism, we can significantly optimize this all reduce, and that gets impact on the overall, like this is a CNTK AlexNet training. So you can see even in the very small scale, like a 224 processes, we can give you like a 9 to 20% benefits compared to other stacks, or even compared to our basic stack where we have not done a lot of these optimizations. So then next we are actually trying to even go further. There are some new designs which have been introduced. I'll not have time to go over it. We presented this. These are scalable and adaptive designs for large message reduction collective. It was a best paper at the IEEE Cluster 2018. So here again, if you see this, this is the solution, what we are trying to use. This is like the purple bar here. Even on like a 896 processes, we are able to push the performance by 35%. Okay. So, and this is not released yet. It will be available in the future releases. So those are the kind of the CPU-based training we are trying to help. So anybody can download our MAPIS2X stack and then trying to get this kind of performance. So the next one is, of course, the GPU-based deep learning. And this is, I think, there is a bigger community which have been running that. And for that, we have a very optimized GPU stack, which is called MAPIS2 GPU Direct RDMA. So before we go into more details on that, let me try to introduce CUDA awareness MPI concept. How many of you heard of that, CUDA aware MPI? Okay, some of you. So in fact, we introduced this terminology in a classic ISC 11 paper, and after that, actually, a lot of people in the community have adopted that, even the other MPI stacks. So the idea is that in the typical GPU cluster, let's say this is your GPU, this is your InfiniBand. Most of the time, you do a CUDA mem copy, then you do an MPI send. Here you do an MPI receive, and then you do a CUDA mem copy. That is the kind of most of the time people use this kind of programming. It will be very quick. You have productivity, but performance might be limited. So what we try to introduce this concept saying, can you have good high performance as well as high productivity? So that means if you're trying to do a user know how to do MPI send from host buffer, can you just replace that with a device buffer? And similarly on the receiver side, you replace the host buffer with the receiver buffer. That's all the user has to do. Everything else, the MPI library will do. So if you take a look at the animation, so within the MPI library, we try to find out how to move the data from the sender buffer to the receiver buffer with the best performance. And in this way, the end user doesn't have to actually worry about, doesn't even to have to know how the CUDA calls happen, how the MPI calls happen. You don't have to worry about. Transparently, they get the best performance and also productivity. So for the last several years, we have been working all our releases. We are not only like trying to continue with this CUDA-aware MPI concept, but also take advantage of all the other features from NVIDIA. These versions are available. If anybody has not used those things, you can just download our versions from our website. Just make sure like you have some of the very latest, the GPU Direct. Even there is a GDR copy library from NVIDIA, so just download our RPMs. You don't have to be even a root user. We also allow the non-root users. So if you have access to any GPU cluster as an end user, you should also be able to utilize our stacks. And very recently, just like last week was the GTC, we presented multiple sessions there, so we made a new release of 2.3.1, so that is the latest release. And in fact, here we have taken a lot of optimizations for systems like DGX2, Power 8, Power 9. In fact, we have a newer support for running TensorFlow with Horovod. I'll try to show those kind of numbers. So we are trying to target both HPC as well as the deep learning through this. Now, if you take a look at the performance, and that's what is very amazing, take a look at this number. So what we are trying to show, this is like the GPU to GPU internode latency. So that means we are able to move data from GPU of one node to the GPU of other node over the network. Look at the number, 1.85 microsecond. Okay. Now, typically, if you see the InfiniBand latency, depending on the MPI stacks, are like 0.9 microsecond kind of things from node to node. And in another 0.9 microsecond, we are able to move data even from the GPU. Okay? So these are very highly integrated design kind of things. And not only like we reduce the latency, small to medium messages, actually we increase even the bandwidth significantly. Okay? And that leads to very good performance. In fact, I'll talk a little bit more tomorrow on that. In fact, we have a very good collaboration going on here in the Switzerland with CSCS, in fact, and Meteo Suisse. Our stack is being used to actually for the real-time weather prediction here. So if you are looking at your iPhone for the weather, we are driving that, okay? So just we are in Lugano here, and everybody looks at the weather. I just want to give that example. But now the question is, okay, how are you trying to help the deep learning? How many of you have used or familiar with TensorFlow? Several of you. So if you look at the TensorFlow, so this is like the TensorFlow started from like Google with their gRPC, but nowadays there are so many different versions, okay? So there is a TensorFlow completely running with gRPC, or it's a gRPC plus X, there is no gRPC, so this is where the MPI coming. So currently if you see 1, 2, 3, 4, 5, 6, 7 different versions are running around there. Okay, so people try to use these. So we did a very systematic evaluation. We have actually a paper coming out. We'll publish, present next month at the CC Grid. We have done a very detailed evaluation with all these combinations. And here if you see the results, so this is the latest, like here we have compared with Horovod, MPI, and Nickel, and especially MPI, we are using our MVAPIS2 GDR stack. So that's what is actually the green bar, okay? So if you see these green bars, and the yellow bar are actually the ideal one, what you can get, okay? So here you can see, like with the green bar, we are almost like getting a scaling efficiency of 90% of what you can get from the basic stack. So once again, I mean, anybody trying to utilize these should be able to download our stack and get this kind of performance. So then what is happening, since this all reduces is very critical to the performance of all these all the deep learning distributed training, we have been trying to optimize that. And earlier I said, like, people are trying to use different message sizes. So here, we are trying to optimize for all message sizes. These are like small, medium, and large. And here we are comparing with 2 other MPI, like a Baidu MPI and then OpenMPI. And as you can see, the MVAPIS2 GDR is very highly optimized and can give you very best all reduced performance, and that can translate to your very good distributed training. And here also we are comparing with Nickel 2. So that is the stack which NVIDIA has been pushing. This is not an MPI library. They're just trying to say the Nickel 2 is the library for deep learning. So we are also trying to optimize and compare. So here if you see, this is on a 16 GPUs on the x86 platform. So here we can say, like, we can give you 3x better performance. Even for very large messages, we can also give you like a 20% better performance for all reduce. And this is the latest on the DGX2. If you remember, like the NVIDIA pushes a DGX2 box, it has 16 GPUs. Again, there also, again, the GPU system is no different. Even though it is a DGX2, I mean, you can run your MPI stack there. So here, we have compared with the Nickel 2 with 16 voltage GPUs. Again, we can see for all these small medium messages, we can give you almost 2.5x performance benefit. Here, even for a 1 meg, 2 meg, 4 meg, we can give you almost 1.7x benefit. So now if you use our stack for actually running so this is the ResNet 50 training using the TensorFlow. So you can see like up to 8 GPUs. In fact, compared to the Nickel 2, so this is the Nickel 2.3, we are just doing the evaluation with 2.4. You can see even with our stack, you can get not only better performance, the higher is better, but look at the scaling efficiency, okay? So that is the most important one, so that we are trying to keep all the network and compute busy all the time using our MPI stack, and we are able to get very good scaling efficiency compared to even the Nickel 2. So those are the kind of the solution, the base solution we are trying to provide, so that if you are trying to use just the distributed training with a TensorFlow, and especially with Horovod or directly go through the MPI, we are able to enable. So this one tries to focus more onto the co-designing, as I was telling, because for HPC folks, people have done co-designing for many years. So we are trying to take similar kind of knowledge to the deep learning. So here we have taken the Caffe. So, and then on top of Caffe, we have done a lot of co-designing so that this is a newer version of, we call it like a OSU-Caffe. This is available. We have a project called High Performance Deep Learning, HIDL, so you can actually download this. And if you use our stack, so you can see very easily, you can move up to like a scale to up to 128 GPUs. Okay, and then get very good performance with this Caffe version, whereas the public version of the Caffe doesn't even run at that scale. So the other thing what we are working on here is this out-of-core model. As I was telling, typically now the distributed deep learning, when people are trying to propose, like let's say I push a lot of images before the operation can start. But then the GPU memories are restricted. Even if you use a voltage GPU these days, 16 gigabytes or 32 gigabytes, that is the maximum you can have. So if your model is bigger than that, it cannot even fit within the GPU, within a single GPU. So how do you do a distributed training? So this is where we worked on something called if you want to train a large model, the issue is becoming out of core. Okay, so that means it cannot fit in the GPU. So in this picture, it says like with a 16 gigabyte limit, I can go up to this much batch sizes, but this becomes out of core training. So here, what we have done, we have used actually NVIDIA has something called unified memory or managed memory. How many of you have heard of that terminology? Okay, so we are using that technique and trying to do a transparent movement from GPU memory to the host memory. So if the entire model cannot fit, so the question is how I can put some parts of the model first inside the GPU and let the training start. And then gradually when it moves to the other layers, we take away the older data and then feed the newer data or the newer layers to the GPU. So through that, we have been able to, again, we have designed an out-of-core Caffe kind of things. This we just presented at the HPC conference. And through that, you should be able to, like in a transparent manner, you should be able to handle very large models. So this is not even released. We'll be releasing it soon. So then the remaining three things. So these are the first three things I said, like more focusing on the pure MPI based. But let me go into the two other things, which are the GPU gRPC. So this is the traditional TensorFlow with gRPC. So TensorFlow came from the Google, and they had the underlying mechanism, which is the gRPC or the Google RPC. How many of you are familiar with this stack? Okay, some of you. So the gRPC, if you go down, this is where you will see, like, of course, it is very portable, but then at the bottom, you will see it uses sockets. Okay, TCP/IP sockets kind of things. And then, of course, sockets, as you know, is not very good performance. Okay? So just like what we have done for the traditional MPI stacks, not only us, a lot of community have moved to native InfiniBand, that's what we have done here. So we took the gRPC layer to native InfiniBand. Okay? So think of like the verbs, which is the InfiniBand or Rocky, think of. So we have taken that to the RDMA-based design. So instead of default gRPC, so you can think of like the OSU RDMA design here. So this is just the gRPC layer evaluation. You can see there is a big benefit compared to the public gRPC version. But now if you put it together, that version, and here we have evaluated this for all different nodes, batch sizes. The red one is our design. Okay? So think of all these things. The red one, we are able to give you the maximum images per second. So the idea is that we are able to run this TensorFlow gRPC at the native, at a hardware layer kind of things. And this version actually we have made a release. So if you, we call it RDMA-TensorFlow Distribution. So if you go to this again HiDL site, so this has the entire RDMA design. It is a little bit based on an older version of the public. It is a 1.3.0. TensorFlow is moving very fast, and we'll try to bring this design to the very latest version. But you should be able to actually run, and we don't change any APIs or anything. It's just the communication has been enhanced, and you should be able to get this kind of performance what we are trying to show. So then the next two things I'll try to indicate, again, as I said, like people are trying to come up with different kinds of approaches. Like sometimes people are saying TensorFlow on Spark or Caffe on Spark. Like if you already have big data analytics environment, you already have the data. On top of that, people are trying to do deep learning. So, and here, so this is the other project. I'll talk more about this tomorrow, and I have talked about this in the prior talks. So we also have another project, high performance big data. It's called HiBD. So there, we have taken all these things, like the traditional big data analytics stacks, like Hadoop 2, Hadoop 3, Spark, Kafka, you name any of these major big data analytics stacks. So these are all RDMA enabled. So that means they are running with native InfiniBand, Rocky. We have support for x86, OpenPOWER. We have support for Singularity and Docker. So again, you can download these versions. Currently, they are being used by more than 300 organizations in 35 countries. There have been like more than 29,000 downloads here. So these stacks people are purely using for big data analytics. Now the question is, can we run deep learning on top of it? And again, if you go and look at the performance of these stacks, so here I'm just trying to show some one or two numbers, like the standard, let's say Hadoop 2.x. What we are trying to show here, it is these experiments are running, like Random Writer and TeraGen are running over InfiniBand EDR, but the difference is that these orange lines are the traditional Hadoop stack. So that means Hadoop is running over sockets, sockets are running with IP over IB. That's what the InfiniBand provides. So you can actually run your traditional stacks, but compared to that, these are our RDMA-enabled stacks. So you can see like we can improve performance by a factor of 3 to 4. So it is exactly the same hardware, but our software is able to give you this kind of performance. This is the Hadoop number. This is like the Spark number. You have the high bench page rank, similar kind of things. You can see almost 37% or 43% performance benefit we can give. So these stacks are already there. We have been supporting that almost for now 7 years. But now on top of these, now people can run the newer deep learning kind of framework. So here what we did, there is a stack called Big DL, Big Deep Learning from Intel. So what we try to run that, there are two lines here. So if you see, this is the traditional Big DL stack, and then which is running over sockets. But now the Big DL stack which is running over our Big DL, it was running over the regular Spark, and now it is running over our RDMA Spark. Okay, so if you see here, you can deliver like almost 2.6x benefit. Okay, and just to highlight, so all these things are, we are trying to accelerate the communication. We are not changing any APIs or we are not changing any accuracy. That's why we show even the accuracy remains the same. Okay, so we are not doing any magic to change the framework or just trying to accelerate the lower layers, which are the communication I/O, so that you should be able to take advantage of these stacks or software in a very transparent manner to get the good benefits. So with this, let me change a little bit. I want to conclude the talk here. So all these stacks, of course, we have been trying to support from the OSU side for many years. But last 2 years, there has been a little bit of changes here, new development. So we are trying to provide commercial support for all these things, our MPI stacks, big data stacks, deep learning libraries. So whatever I've been talking about is actually, you can actually get it through this company called Xscale Solutions, so which is also a sponsor of this event. And I have a booth outside. If some of you are interested, you can actually stop by and talk to me. So actually through these, for last 2 years, we are actually supporting the entire computing infrastructure for Lawrence Livermore National Lab in the US. So you can get a lot of these kind of things, very application-specific optimizations, customized tuning, very rapid response time for your issues. Whatever you need for a production environment, we are able to do that. In fact, recently, we have become a silver ISP member for the OpenPOWER Consortium, so that all our software stacks can actually be tested, validated against the OpenPOWER stack, and we should be able to distribute on the OpenPOWER ecosystem. So these activities are also going on. So I just wanted to show these things so that you are also aware that it is not only like things are being available and being used in from a research side, but these are also the commercial side things are available. So with this, let me conclude the talk here. What I presented is more like started with the need for scalable and distributed training. Of course, all these things require high performance middleware designs and also co-designing to get the performance. And here I gave you some different kind of solutions. And these solutions are mostly like optimized collectives for CPU-based training, CUDA-aware MPI with optimized collectives, TensorFlow, and also the DL support for big data. So it doesn't matter which you are trying to go for your deep learning, we have the different libraries and stacks available for you so that you can utilize these to accelerate your distributed deep training. So with this, let me thank all our sponsors of our research, but most importantly, these are all my heroes. I just come and give talks, but a lot of these talks, whatever I told, like 24th talk, this is the 24th talk, these are the people who do all the hard work. Past student, staff, current student, staff. So I always give credits to them when I give this talk. So with this, let me conclude here. These are all our web pointers, and I'll be here today and tomorrow. So if you have any questions, quick questions now, I can handle it. Otherwise, if you want to discuss it offline, I'll also be very happy to discuss with you. Any quick questions? Yes. This one? 34, okay. Yes.
So here you are comparing inter-Caffe optimized,
yeah.
OSU-Caffe optimized, and you say it's 80% better.
I think this was like the standard, I think it was the basic InfiniBand, I think ADR. InfiniBand ADR with a Broadwell kind of cluster, okay? Because we could not, because these are out of core, so we cannot actually show, these jobs cannot run on the GPU cluster, so as a reference, we just compared it with a CPU-based training, which you can run on the CPU side. So that was like a reference, numbers kind of things we're trying to show. Any other questions? Okay, so if not, thank you.